mean, I wanted to participate again because I really liked it last year, but this semester has been crazy, so I can't really. I'm going to be traveling again, and then things are all over the place.
Should I also write the out or read this?
No, you can say my words what the others say. Oh, by words, you don't need to write them down.
Okay. Oh, just write it. I don't know which one's the last name, which one's the first name.
The other way around. But that also works, but it's the other way around. Yes,
Like this?
I think so.
Okay.
Now you can turn it on. You can turn that on. Put it in your pocket. On top, in between the two. Yeah.
Oh, it's already.
It's already on.
It looks so.
That's scary. Okay, you can put it in your pocket. It's simple.
Oh.
Very good. So today Marvin will tell us about something that is related to this paper of 7 katana.
Okay. So the first thing I will introduce is this idea of higher form symmetry breaking and high force symmetry, which is a generalization of global symmetries. And the motivation to introduce this idea is that it may be able to encapsulate more complex phase transitions than the usual phase transitions that are accounted for in the usual paradigm of Landau phase transitions. So like topological phase transitions and more complex phase transitions do not fit in the regular global symmetry breaking paradigm of Landau. And it works as follows. We can also call it a p-form symmetry. And the idea is that a global symmetry is a zero force symmetry, a regular global symmetry. And the intuition would be that zero force symmetry has charged operators that create zero-dimensional objects. So and in this paper we talk about a one-form symmetry, and the intuition will be that the one-form symmetry has a charge operator that creates one-dimensional objects. And first, before I introduce the model, which we will be talking about, I will introduce a result that is derived from the theory of high-form symmetries, which is the following. For a regular global symmetry, we expect that an order parameter in the unbroken phase will behave like this if you take two faraway points in the system. And in the broken phase, it is expected to factorize, and it behaves as a constant. And the analogy in the case of a more general high force symmetry is that this equation, instead of talking about a local order parameter, you should talk about a charge operator that is extended. I will call it W of C, where C will be some kind of region that is parameterized by this operator. In this case of a 1 for symmetry, it will be a string. And so in the unbroken phase, for the high force symmetry, you expect the charge operator to behave like this. Where this is the area that is encapsulated by the curve, in this case of a 1 for symmetry. And so this is the unbroken phase behavior. And the broken phase behavior for the relevant operator should scale with the perimeter of the region that the operator, the relevant region of the operator. And the easy way to see that this is analogous to the global case, even though it don't look like, is that in the global case, in the broken phase, we have a factorization, so it don't depend locally on the relevant charge operator. And here, in the 1 for symmetry, what happens is that it only depends on the perimeter of our string, so it depends locally on our string instead of on the area, which is non-local, which is analogous to this dependency on the distance between the operators, which is also a non-local dependence. So this is the way to see the analogy between perimeter and the constant behavior and this and the area, is that in this case it's factorized and only depends locally on the curve. Okay, so to see an example of a system that displays one-form symmetry breaking, the authors of the paper introduced this model, which is given by this Hamiltonian. I will explain it what this means right now. I just need to draw a lattice. Where these taus are actually Pauli matrices normalized to 1, so without the regular 1/2. And I'm calling it tau instead of sigma because I'll introduce sigma Pauli matrices later. So this model has spins living on the edges of a lattice. And okay, I'll not draw all of them, but the idea is that this term is some kind of like external fields that couples at every edge of the lattice. Let's draw, I call it E. At every edge, the spin couples with like an external magnetic field or something like that. And this is a plaquette index. So for every plaquette in the lattice, the 4 spins that live in the boundary of the plaquette, they interact with a Z Pauli matrix, and the coupling is K. Okay, so the idea is that this model will display one-form symmetry breaking so that you can see this at play. Okay, so to see this, we first need to define a one-form operator that will behave like this when we change phases. So first I'll write the operator, then I'll give some intuition why we choose our operator like this. So the operator which we use is it is an operator that will depend on a closed loop in the lattice. So I will call this the path gamma. I guess I will just write a gamma index here. And for every edge that gets crossed by the path on the lattice, we will multiply the Pauli matrix in this direction. And we take this product along the path. So for instance, if you take a path along a closed loop around the plaquette, you just take the products of the 4, like this interaction term right here. And okay, so what's intuition? Why we should expect that an operator like this, at least there's an intuition for it having a phase transition behavior. So let's take 2 limits in this Hamiltonian. First, let's take, before I take this limit, let me introduce another way to write this operator before I take the limit. It will be more instructive. So I write it right here. So I will draw a path. This is our curve gamma. And I will now draw the rest of the lattice in like this, okay? And taking the operator W that I'm writing is the product of tau z at every edge that's crossed by the path. But I will show you now that you can write this instead of the product of the plaquette operator, this plaquette operator right here, in all the plaquettes that are enclosed by the path gamma. So the idea is the following. Let's take the plaquette operator in this plaquette and the plaquette operator in this other plaquette. So the product of these two plaquette operators will have one contribution from this edge, one from this edge, one for each one of these edges. But this edge right here, that is between two plaquettes, will will be quadratic, right? And since the square of the polymatrix are 1, it is the same as if we didn't include this in our product. Okay? Makes sense? So if we continue to do this to include all plaquettes that are inside the gamma contour, then all the internal ones will go away because it will be in two plaquettes and will be 1, and we are left with only the contour. So what I'm trying to say is that we can rewrite this operator as also the product in the plaquettes inside the curve gamma of this operator right here. So I'm doing a product in all the plaquettes inside the curve. This is only the edges. It's the same. Okay, so with this, we can see the following. If you take the coupling K to be much, much bigger than the coupling J, so let's ignore this term, and we see that what happens is that the system will tend to maximize the value of the plaquette operator. So every plaquette operator will have value 1 in this limit. And thus, since we can write this operator as the product of the plaquette operators, this means that this operator in these limits in which K is much bigger than J is just a constant 1. Okay, so W approaches 1 in the limits in which K is much bigger than J. However, let's take a look at the other limit. If we take J much bigger than K, then this means that every edge, now we will use the edge representation, which will be more convenient. If you look at every edge, it will be an eigenstate of the X polymatrix, which means that the expectation value, sorry, I forgot to write the expectation value, which is important in the definition of the operator. It means that the expectation value of the Z polymatrix at every edge will be 0, because it will be all tau X eigenstates. So since all of them will be 0, this means that the W operator goes to 1 in the other limits, with J is much bigger than K, independent of the path in this case. Okay, so we see that we have a kind of behavior which resembles some kind of symmetry breaking when we take two different limits of the system. Okay, so now to proceed, I will introduce a duality which the authors use. So that we can actually get some intuition to how to calculate this operator.
Leave those some formulas, please. Don't raise those.
This?
The last two formulas.
Okay. This one okay. This one are actually important. Okay, so the duality will be the following. We only have white. So the duality will be with a dual lattice. So we have a dual lattice in which vertex of the dual lattice live in the center of the plaquettes of the regular lattice. And we will define an Ising model in this dual lattice. And the way in which we define this Ising model is the following. At every edge of our lattice, the edge operator in the x direction, we will it will be associated with the product of the z direction operator of the spins living in the dual lattice. So I write down this. So, and now I'll call this sigma instead of tau to make it clear that I'm talking about this other lattice, which is the dual lattice. So the idea is that every edge determines two nearby sides, and with this we can associate to a coupling between near neighbors in an Ising model. So we can do this in the vertical and in the y and the x direction. And the other component of the duality is that we will associate every plaquette operator with the x direction spin operator of the Ising spin that lives in the center of the plaquette in the dual lattice. So it will be plaquette I, sigma I. So I will not prove this duality. I will just use this as the use in the paper. But the idea is that this is actually a duality transformation. And using this duality transformation, we can see what happens to the Hamiltonian of the system. So the Hamiltonian, the dual Hamiltonian, we see that we get this, which is the non-transverse field Ising model. And in the transverse field Ising model, we know that in the limits j much bigger than k, which this is more easy to see, we get the following behavior for the spin-spin correlation function. So it should appear a constant, right? Because the spins should all be aligned. And for k much bigger than j, what we should have actually is that if we talk about the z direction correlation, which is the one we are interested in, it should go to 0. So we see that this has the exact opposite behavior as the behavior of the W operator in the limits of when you interplay the hierarchy between j and k. So since this has the opposite limit, you can start to wonder if this operator has something to do with the disordered operator that we saw last lecture. And the answer to this question is yes. And to see this, look that when under the duality transformation, the operator W gets mapped to an operator on this Ising model, which I call xm, which is what? Since you can write the W operator as the product on plaquettes that are inside gamma, and we define in the duality transformation a product of a plaquette, it's just the sigma x spin. This means that we just need to look at the curve gamma, for instance, that the operator is associated to, and inside gamma we take all the spins of the regular lattice and take the product of the spin operator in the x direction. Okay? So I'm just using the duality transformation in the definition of W, so that it maps the plaquettes inside the contour into just gamma x. So this operator will be a product at every side inside the curve gamma of sigma x at that side. And now, to get intuition to what this operator does, let's take a state, an z direction eigenstate, like all up states in the lattice, to get a feel to what this operator does. So suppose all these crosses are an upspin. If I choose the curve gamma to be this curve right here, for instance, sorry, the curve is on the dual lattice. So if I choose the curve gamma to be this, for instance, This means that every spin inside the curve should get acted by a sigma x operator, and when a sigma x operator acts on an up spin, which is a z eigenstate, it just flips it down. So the effect of this operator in like a all up state is just create a domain wall inside the curve gamma, because it flips all spins inside and do nothing outside the curve. So this operator actually creates domain walls in the dual system, which is an regularizing system. Okay, so this is the field for the W operator, and then finally, what the authors what they do is that they use this representation in the transverse field Ising, which is easier to simulate in a computer than this model right here, to simulate this operator xm in regimens in which k is much bigger than j and j is much bigger than k, and they obtain exactly this behavior right here in the corresponding hierarchies. They obtain this behavior right here in the unbroken phase, and they obtain this behavior right here in the broken phase using the duality, so using the dual model, because it is harder to simulate in this model right here. And then the punchline is that they see the actual behavior of the high force symmetry in practice in a physical system in a non-trivial way, which, as they say, is something that, like this high force symmetry thing is a new thing, which not many systems were put under it was not tested in a lot of systems. So the idea is that they would test this in a system to show that it works. They get exactly the scaling which the three predicts. One goes with the area, the other goes with the perimeter of the curve gamma, and I guess this is it.
Thank you. You guys have questions? Otherwise I can ask. What do you think? What's the connection between those continuum limit formulas and the formulas on the right? W equal 1 and W equal 0. How do I see that this 1, 0 are related to this area and perimeter?
Okay, so the intuition is that when W approaches a constant, as our intuition says, it should be the broken symmetry phase, right? Just like the regular zero, the regular global symmetry, when it approaches a constant at long ranges, it means that the symmetry is broken, spontaneously broken. So it approaches 1. And you see that this behavior right here has a smaller decay, typical smaller decay, than the behavior of the area, because what the authors actually do is that they parameterize by a square. So the area is like L square. So you could have like L square and L. And the idea is that you should expect a faster decay in the unbroken case, which is the area, and a non-faster decay in the broken phase, which goes with the perimeter. And the idea is that here, okay, like 1, 0, the other is 1, but I guess they say in the paper that there is a way to remove the perimeter dependence right here, but I didn't understand it very well. But the idea is that this one this one should decay faster than this one. The one that goes to 0 should decay faster than the one that goes to 1. And it's the corresponding which one goes with the perimeter, one goes with the area, and the area is bigger than the perimeter, so should have a faster decay.
Can you add broken and unbroken to the equation of the sigma?
Of course.
And the one on the right as well.
This?
Yeah. What happened there? I'm confused by that.
By the broken and unbroken.
Why did it change? We agreed that it was J much bigger than K, that it was broken, and now it became...
Oh, so that's what I try to make an intuition that we see. The behavior here is exactly the opposite behavior as the W. The behavior of the sigma correlation function it's exactly the opposite behavior of the W. So
That is a definition of what broken and unbroken means, but I find it very confusing because if you have a duality, it's a bit funny to call broken phase
I see.
two opposite things. I mean, if you say J much bigger than K is broken,
I see.
you want to change name and to say.
Yeah. It's
Otherwise, how do I make it? If I need a broken phase, now I don't know.
no, okay, you are right. I should clarify. Yeah, I should clarify what I mean by this is that in the perspective of the W operator, this is the broken phase, and this is the unbroken phase. And on the perspective of the sigma correlation functions, this is the broken phase, and this is the unbroken phase, and they are opposite behavior, which is what makes it clear or suggests that this W operator is related to the disorder operator.
You should put broken heads and unbroken heads.
Okay.
It's broken of the dual theory and unbroken of the dual theory. And then you can say broken head is unbroken and unbroken head is broken.
Okay.
Right? Because that's what the duality does. It swaps
Mm-hmm.
order and disorder. I think I like very much your presentation. I thought there was something that could look misleading for people that were in the previous talk, but no one was in the previous talk, so I think it's probably not misleading, which is you said that you flip all the spins inside, so it's like a domain wall, like the one we saw in class. But there's a very important difference, right?
Mm-hmm. Yeah,
This model and the one we saw in class.
this is a quantum model, and the one you saw is classical, and also the one you saw in class, it just flipped the coupling along the path, right? And okay, you have like a big region inside. Oh, I guess it does the.
Oh, that's good, because we agreed that flipping the
Mhm.
couplings at the boundary is the same
Sim,
as
sim.
flipping all the spins
Yeah.
inside. So that's
Mhm.
fine. That's okay. But it's quantum.
Yeah, it's quantum. I should have made it.
So
more.
what's the relation to a classical model? If you wanted to relate this to something classical like what we saw in class, what would you say?
Well, I would say that this correlation function is analogous to the classical spin-spin correlation function, and that this W non-trivial, very non-trivial operator is related to the mu correlation function that we saw in class.
Yeah.
But the important difference is that this is only defined, I only defined it in closed loops, and the mu correlation function, we defined it in generality in any path, so that's a difference, but I guess the long range behavior kind of mimics the one of the mu correlation function, as it behaves in the opposite way as the sigma correlation function, just like the classical model we saw.
More questions? Okay, so let's thank Marvin. Let me make just a few comments about what you said, which is the following: that here we have a duality between these two quantum models, right? Where this is a two-dimensional quantum model and this is a two-dimensional quantum model, right? In class, we saw a duality between a one-dimensional classical model, a two-dimensional classical model, and a two-dimensional classical model, which was this high temperature, low temperature duality. And there, what we saw in class, so this is 2D quantum, and this is 2D quantum. And just to connect what we saw in class we saw something between a 2D classical model with some temperature T and a duality between a 2D classical model with high temperature. So this low and high temperature is very much the analog of this swapping J and K, so that's the same thing. But there we have two classical models that get swapped under this duality. And here you have two quantum models. So actually, what happens is that this two-dimensional classical model is equal to a one-dimensional quantum model. So you can translate two-dimensional lattice models. You think that the 2D lattice model, you have a lattice here, and then you have a transfer matrix that involves the system in this Euclidean time. And you can take a continuum limit where you replace this time evolution, this by transfer matrix time evolution, by an Hamiltonian, and that defines a quantum model in one dimension. Because now we have our space is here, 1D, and then we have time. Now, if you do it, you start with a model that only had classical interactions and it was isotropic, time and space was the same. But in taking this limit, the theory looks different and it doesn't look exactly the same. And when it does, it looks like this model. So the model that you get, the 1D model, is actually exactly this Hamiltonian H star, where the only difference is that it's in 1D and not in 2D. So this I and J are neighbors. And so this 1D quantum model here, this model but in 1D, is equal to the 2D model we saw. Okay? And then this one here, by definition, is equal to the same 1D quantum model, because this model is the same as that one. So here the duality is the same H star. The only difference is that some T got transformed into this dual temperature T prime. And so, in this case, you would say that these quantum models, there is a duality between the two models, but it's more like a self-duality. You have a quantum transversizing model is self-dual to a quantum transversizing model. Here, a quantum transversizing model in 2D, it's not dual to itself with K and J replaced. It's dual to this model that we would call the Z2 gauge theory. So this quantum Z2 gauge theory, it's dual to this quantum transversizing model. And indeed, this model, you can relate it, instead of going from 2D classical to 1D quantum, you go from 2D quantum as a 3D classical model. And that's the 3D Ising model instead of 2D. And then you can also define a dual of this one, which is a 3D lattice gauge theory. And so in this case, in 3 dimensions, you don't have this low high temperature duality at the classical level that relates the model to itself. But it relates the model to another description of the model that looks different, that looks like this gauge theory. Okay? And so, yeah, so these are all true statements. Yeah, okay. So I thought it could be helpful just to connect to what we saw in class.
So even though things are a little bit very different, in class we were in this classical domain, and you went, if you want, to one dimension higher, or to the quantum, which is the same. But otherwise, indeed, the ideas are very similar. Okay, and actually, okay, so these were all comments on your presentation. So we should try to ask the video to be cut and this to remain in your video. So, yeah, if you could remind me or send me an email asking me to make sure that this part is in the same video as your video, because we'll break the video, Susan's presentation and my presentation. So maybe this is better to stay after your presentation. Okay. So now, this is actually quite useful, what you did, because many of these things will show up now where we describe the paper by Wilson, which introduces exactly what is a lattice gauge theory. And so, we already saw in your presentation one example with these plaquettes and this notion that when you have a plaquette, you multiply things along the links that bound this plaquette, and so this is exactly the kind of ingredients that Wilson introduces. Okay, so so the idea is the goal is to understand or if you want, find a theory or maybe even better, an approximation to understand, find a theory or find an approximation of why the expectation value of the Wilson loop, which is defined as you explained by some curve C, why this will be given by exponential of something times the area of this Wilson loop. Now, let me explain why this is the goal, but this is the goal, which is how do I find a way of understanding why this curve of observables would be related to the area that encircles this curve. Okay, but let's first motivate it, following what Wilson did, and let's remind ourselves of a system where I have a quark and an anti-quark, or in a toy model I could imagine a scalar and a charge scalar inserted at some position 0. And then these guys, they propagate following some paths to some scalar and its charged scalar at some position x. And you want to ask, are they confined? Namely, when they fly, are they far away or do they stay together? Right? And the idea is that this propagation, you see the quark went in one direction, I could think the anti-quark went into some opposite direction. So you see that here in this picture, we see some curve C appears. And indeed, we'll write a formula where this expectation value will be related to the expectation value of the Wilson loop encircled by this path of the quarks. And so if this path is suppressed by the area, it doesn't let the quark and anti-quark get separated, they always stay close. Because they want to suppress this path as compared to a path where they stay together. Right? This would have much smaller area. So if our Wilson loop is suppressed by the area, then it will not let the quarks or the charged particles deconfine, separate, and it will keep them together. Okay, so let's recap how we see this. So this is the path integral over some scalar fields and over some chromodynamic gauge fields that I have in my theory. My action e to the minus integral of the gauge field kinetic term plus the scalar kinetic term. Let me write it like this. And then I'm computing the expectation value, so downstairs I put phi of 0, phi bar of 0, phi of x, phi bar of x. Okay. Yeah, that's it. Okay. And now, so what we do is, let's leave this to the end. So this we do at the end. The path integral over A. From the point of view of the path integral over phi, this is just Gaussian. So all we have to compute is the propagator between these fields and the propagator between these fields. So here we have some propagators, something like going from 0 to x of the inverse of this kinetic term. Okay? So far so good? Okay, so I'm just reviewing now some basic stuff about and we have this guy and we have the complex conjugate of it, so it would be the absolute value square of this quantity for the two propagators. Okay, and now this guy is equal, and maybe I can give some details, but maybe let me first write down the result and then we see if we need details or not, to the following quantity. If I want to study this propagation from 0 to x, I integrate over all paths y of t such that they start at y of 0 equals 0 and they go to y of capital T equal x. So all paths that connect the points 0 and x, these are of course vectors, we are in the dimensions. It takes time t, so I could also say I integrate over t, over how much time it takes. And then I would get exponential of minus the mass times the length of that path, which is the integral of square root of y dot square dt. So that's the length of the path connecting these 2 points, plus the integral of the chromodynamic gauge field, A mu, evaluated along the path, y of t times y dot mu dt. Okay, so just a few words. So, first of all, is the statement clear? This propagator is equal to this statement. Is it precise? I integrate over all paths y that go from, this is one y, this is another y. I integrate over all y's that connect 0 and x in time t, and I have the length. This is the length of that path. Gamma parameterized by y of t, gamma prime parameterized by y prime of t, and then I have a coupling between the gauge field and the path. So first, let us note that this is a function, this stuff here, is a function of the path. It's not a function of y of t. Namely, if you change y of t, if you change t, your parameter, to some other function f of t, that is a different parameterization of the same path, so if you break the path like this, versus if you put many more points in some region, it doesn't matter if you do t to f of t. We see it explicitly, because you see you have derivative with respect to time times dt. So if you change t to f of t, you get an f prime times f prime, it cancels. Here as well, you get f prime squared, but inside the square root, so you produce an f prime that cancels with the change of variables. So this is invariant, is parameterization invariant. It's invariant under changing time to some function of time. Right? So that's good, that it's really a function of the path. Now, what was done to go from this representation to this representation? It's the usual thing. I have this operator here, which is 1 over, let me first write without the a, just to remind you how it goes, then putting back the a at the end is easy, so derivative is p squared plus m squared, and then you say that this is just the integral of e to the minus t times p squared plus m squared, right? And so you have this operator. This is what this operator is. It's just some exponential representation. And now you have a time evolution. You evolve for time t this operator. And how are you going to do it? You are going to just evolve it from one point to another point by inserting the identity a bunch of times. You discretize this t, you break t into n times epsilon, where epsilon goes to 0 and this guy goes to infinity, and then you insert the identity at each piece, and you insert a bunch of identities at each instance I. You introduce a metric that tells you where do I put the points, but nothing depends on that metric. You integrate out that metric and you get this expression. Okay, so this is relatively straightforward. This is just, I'm just reviewing, but that's it. So you write this as a product, e to the minus epsilon, p squared plus m squared, and now in between each epsilon, you insert the resolution of identity, and so on. Right? Any question? Now, if it was non-abelian, if this field was non-abelian, if this guy A in a non-abelian gauge theory is a matrix, right, like in QCD, then we have to be a bit more careful. For example, here we will say it's trace of f squared, not just f squared. And then it's not, this is a matrix, so this by itself doesn't make sense. So I cannot write this exponential times this exponential. This is exponential of a matrix. So I need to be careful, and I need to define this object, which is the path order exponential. Okay, so let's define what this object is. But let's write the final formula. The final formula is that this correlation function would be the integral over all path y's that are closed, because we have one going and one coming back. So these are all the paths gamma that go and come back. And then we have the expectation value of this Wilson loop that depends on the curve gamma, weighted by e to the minus the mass times the length of the curve gamma, where what is this symbol? This symbol is the average over all gauge fields, that's what I said we will do at the end, of the path order exponential of the integral in this closed contour gamma of this matrix A mu that depends on evaluated along the contour. And this is a matrix, and so we will take the trace of this object to make it into an anchor. Okay? So that's the definition of the Wilson loop. So it's an expectation value. There are two things: expectation value, that is obvious. The action involves e to the minus trace of x. So this expectation value, okay, that's hard to compute. I have to do a path integral, it's complicated for an abelian gauge theory. Then there is this definition, and this definition there is a trace, that's easy, and then there is a path order exponential, and that deserves a few words, and I'm going to spend a little bit of time defining more careful what this object is, but this would be the Wilson loop depending on a contour gamma. Okay? And as you see now, if this is suppressed, then it means that the paths where the particles get separated would be suppressed, and the quarks, or in this case the scalars, would be confined and would not separate. So in QCD, we believe this is suppressed. But we don't have a good approximation to compute. If I just tell you compute this Wilson loop, you don't know. It's complicated. It's strongly coupled. You can only do perturbation theory, but then you don't know how to compute the flow when you compute a big Wilson loop, and you cannot do it. So we cannot compute this object. I cannot tell you exercise, compute this object, because it's strongly coupled. It's hard. Okay? And that's where we need to use computers, but we can only use computers if we understand what kind of approximation can we do, and that is what lattice gauge theory is. So it's finding a way that we can try to see that the Wilson loop is suppressed by the area. Okay. So let's define a little bit what this Wilson loop is. This symbol, expectation value, is what's related to this average with this measure, right? So that's what the symbol expectation value is. But I care for now about defining what's inside the expectation value, which is the Wilson loop operator, which is the trace of this path order exponential and so on. So let's just define this object here, which without the expectation value, this is just what the Wilson loop would be. So we want to define this operator and then find a way, an approximation scheme where we could compute its expectation value, and show that it is related to the area encircled by a curve and not by the perimeter of that curve or by something else. Okay. Any question? Okay. So, do you know what the definition of this object is? Should I just jump over it or should I explain? Do you know? No? Okay. So, one definition comes, if you want, from just following the steps that I said before. If you want to define a Wilson loop and you have a given path, you just first break the path into many segments. By the way, note that what we have is a closed path. That means that the end point and the final point is the same, but it doesn't affect what I'm saying now. I can do it, but it's open. So there is this beginning and end. It's a marked point on the closed contour at this moment. And so now what do? I discretize like this. So I have some size epsilon. And there will be some limit when epsilon goes to 0. of this picture. And what is this picture? This picture just means that I multiply starting from, say, A all the way to B. I multiply e to the epsilon, I discretize that integral, times delta y mu at position. You see? So I just discretize and multiply. And this is a matrix. So this is a matrix. So the order matters. I start with point A and I go all the way to point B. But this is a matrix, it matters. And the exponential of a matrix, e to the matrix, is just defined as identity plus matrix squared over 2 plus etc. And because we discretize, in practice we only care about the identity and the linear term. Right? But we need to take the limit and we need to multiply many of them. Okay, so that's one definition. And now with this definition, it's easy to see that this Wilson loop, that for now it's a Wilson line, for a contour that connects A going to B, now it's an open line defined like this. It could be A going to A, if B is equal to A, but otherwise it's A going to B. It depends on the path, gamma, but it depends on the initial and final point. And indeed, if you do a gauge transformation, for example, imagine the theory is a billion. If the theory is a billion, you change A by A plus derivative. A plus derivative is A at the final point minus A at the initial point of the segment. All they cancel in the middle, initial and final, they can, except the first and last one. And so you get it under a gauge transformation. If you do it carefully, you get the gauge parameter evaluated at point A times the Wilson loop times the inverse of the gauge parameter evaluated at point B. Everything in the middle cancels. So this Wilson loop is not gauge invariant. Under a gauge transformation, it transforms with this. But you see that if you take now the Wilson loop, the Wilson line from A to A, across a post gamma, then it's almost invariant. There is omega and omega minus 1 at the end at the same point. And so if you take the trace and you call this the Wilson loop of gamma, now this object is gauge invariant. It's a nice gauge invariant operator. And that is what that object is. Okay, good. So gauge transformations, they transform this segment. Again, at each point you pick an omega and an omega minus 1. But because of that, when you multiply many of them, this omega and omega minus 1 cancel, and you only are left with an omega and an omega minus 1 at the end. And then when you take the trace, they all disappear. And that's one definition of this Wilson loop. Okay. I think I'll stay with just one definition. I was going to give you equivalent definitions and leave it as an exercise to show they are the same, but we don't need it. We just have these definitions. And the basic idea now is to think that now we are going to think of this object as a U variable. It's a little bit, it's not an algebra element like A, it's a group element, it's an exponential of A, it's a bit of A. And we are going to think that this U variable will live with some lattice, and it will live in the edges of this lattice, and this U variable in this lattice model connects point X and the neighboring point X plus in some direction mu. This could be some 3D lattice, right? So I have a point and then a direction. And I think of this guy here as basically the exponential of the gauge field here when the path is vertical, for example. And so we will have these U operators that will live in the links of some hyperlattice that could be 2D, 3D, 4D, depends on our dimension of space-time. And the idea is to replace our action, which is some integral over space-time of some Lagrangian, replace it by a sum over some lattice points of some discretized Lagrangian that will depend on these U variables instead of these gauge fields. Such that we will go back from this to this when we take a continuum length. But where this guy would be under better control to answer questions such as confinement by using arguments similar to the ones that Marvin used to argue that the Wilson loop to have to be area law in his case. Okay. So let's write this model down. So the proposal is what we give the name lattice QCD, where we have a partition function, which is where we have the integral. Now remember, before the spins in the previous lecture were plus minus 1, but now we have for each edge E, we have to integrate over this matrix du at edge E. Now, when U is a group element, this is not a matrix, it's not a good measure for the group. The good measure for a group is what's called the Haar measure, which is the trace U minus 1 du. So you see that, for example, if we do a billion, U is e to the I phi, and then this guy is just d phi. Right? And U minus 1 is just e to the minus I phi, and this is just multiplying the phase, integrating over the phase of the at each point. Okay? For edge. Okay? So this would be the measure of integration. And then the action would be exponential of the sum over plaquettes up here. But sum over plaquettes, exponential of sum, I can write as product over all the plaquettes P. So P is plaquette. It's exactly what was plaquette P is surrounded by some edges. And then, so this plaquette, another name for it is a face of this lattice. And then we have exponential of 1 over g squared, the coupling, which would, by the way, in the previous formulas I forgot to write it, but it's there of course. And then we can say that we have a sum of I remember now. Okay. So n will be a point of this lattice, a point like this, n. And let's see why this is obviously a plaquette, because now I write the following. I write the sum over mu and nu of the trace. Now let's write this down. U and mu. So this would be, I start at m and go in direction mu. After I do it, now I am at this position, which is n plus mu, and go in direction mu. After that, I am at position n plus mu, and go in direction minus mu. And then, at the end, I am at position n plus nu and go in direction minus nu. Okay? And that's the action that we would write for the for our gauge field. And if there were some quarks, we would add them as well. I would write times the exponential of the sum. And now I would write a quark bar at some position, u at some coupling these two positions, and then quark at the other position that is coupled by this u. Okay, and finally, if I would also add, this would be with some constant plus a sum of psi at the same point, and this is with different constants, kappa prime. Okay? Good. And so that's, if you want, the definition of our model. And now, why is this a good definition? Why do we like this definition? Well, if I write that u is something almost the identity, if u is something like this, if this was true, if u at each edge was almost the identity, was 1 plus identity, then you could see that if you plug here u equal exponential of epsilon times a, what you can see is that this term reproduces precisely trace of f squared. Okay? So namely, you see that you have a at a bunch of points, so of course derivatives of a appear, and so what else could it be? This is the lowest thing you could write down, and indeed it is what you get, and it's the lowest thing you can write down that's gauge invariant. This is manifestly gauge invariant, right? Because each u transforms, but it's a closed contour, so in the end this doesn't transform. So it's gauge invariant, it's something related to a and its derivatives, and I expand, so this is the lowest thing I can write, and if you do a computation, you see that you get exactly trace of f squared, where f is what it is. If you want, that's the definition of f. It's defined as the object that you get when you take this connection and carry it around the closed contour. Okay, and so this section, and then these terms here, similarly, these terms would be related to psi d slash psi in the continuum limit. Right, when u is very close to the identity. Because you see, you get psi at a neighboring point, that's related to the derivative, but you also get psi, a times psi, that's related to the slash. Okay, so if you tune k and k prime, you can get exactly psi d slash psi. Now, of course, that's a big if. That is, if there is a regime where if this would happen, if by tuning G there is a parameter where U is very close to the identity, then the theory becomes the continuum theory, right? And then if that was the case, this theory in the continuum limit would converge to the theory we want to study. But then we could study other strongly coupled regimes where it's less obvious what the theory wants to do. Okay, but that's, if you want, this is what is called the weak coupling continuum limit. And that is, if you want, why we believe that these actions are a discretization of the usual actions. Again, it's important that these parameters, fermions live at the links, at the cusps. Gauge fields live at the links. The transformation of this U parameter is omega at the endpoints of the link. The transformation of the fermion is just omega at that link point. And so when you write something like a fermion psi bar followed by many U's and then fermion, this is gauge invariant. Because this guy transforms as omega minus 1 times psi bar. Then the next U transforms as omega U omega minus 1, etc. And the last guy, omega U omega minus 1 times omega psi. So all the omegas cancel and this object is gauge invariant. And so we have two types of gauge invariant operators. We have closed loops of pure blue. So these are related to Wilson loops on some contour gamma. That's a nice observable. Another one are these meson-like objects where I have a quark, psi bar, and psi that I could write as psi bar times path order exponential of the integral from point A to point B psi. Right? Where I write a line operator. The line is not gauge invariant, but I stick a quark and anti-quark, and now it's gauge invariant. And so there are these two nice observables, closed loops and open loops. And now I could ask, how do I compute expectation values of these closed and open loops? And yeah. Okay. So that's the definition. Okay. Any question? Is it clear so far? Okay.
I always introduce Wilson loops by talking about quarks, but in the period in those cases it should still be confined, like it's the theory of colorless blue balls.
Yeah.
And is it wrong to also like argue this in the same way that the Wilson loop expectation is an area law on the left?
Yeah, if the Wilson loop expectation value is area law, that's the definition of confinement. And you would say that it tends the loops don't want to open, they want to form these clumps, and the clumps are like the blue balls. Right, so if you let the chromodynamic gauge fluctuate, instead of forming big loops that you sum over, you just sum over small loops, and the small loops are blue balls, which are particles just made out of glue.
So it's just historical that the interest first was in quarks?
Yeah, because blue balls are unstable and quarks are stable. Mm-hmm.
Sort of something that's I've never really understood about lattice theory is sort of how does gauge fixing work here? If you wish to sort of give this, presumably you need to fix the gauge somehow.
So here we are not worried about gauge symmetry, we are just saying U is some, imagine it's a U1 theory. So the integration over U is finite. It's not non-compact. I integrate, say, from 0 to 2 pi. And I don't care if there is an overall big number that I produce, because I'm going to compute the expectation values and I'm going to do z with something divided by z without something, and that just goes away. So we need to fix a gauge symmetry when not fixing leads to divergences, and because there are infinities that we don't integrate over. If the gauge group is compact, you can gauge fix, but you don't need to.
Right. But presumably it's still, well, for computational purposes, you'd like to not have to sum over the real unit round.
It's not obvious. Sometimes yes, sometimes not.
It's just because I've seen people talk about sort of ghost propagators being computed on the lattice, and to me it's a bit.
Typically, when they discuss these propagators, they are not gauge invariant.
Right.
Then you should not discuss.
Okay.
Yeah, or you should be very careful when you try to take conclusions out of them. You should first construct a gauge invariant quantity out of them, and then discuss physical conclusions. Okay. So, what is our Wilson loop? Like we said, the definition, it's a product of many small elements. We multiply this guy many times. So what's the definition in the lattice? We just multiply along some contour, like you were doing in the first presentation. So now our Wilson loop that depends on a contour gamma is just, I have my lattice, and my contour is just some curve on this lattice. Right? And so I just have some contour gamma. Right? And now the definition is just I multiply along the curve gamma the U operators at the edges that are in this curve. I multiply all of them. And then at the end, to make it gauge invariant, I take the trace. Just to understand better, in the abelian case, this would be just the exponential of the sum over all the edges that are in my contour gamma of the phase of this edge E. I multiply e to the I phi at each phase, and the multiplication of them is just exponential of the sum. And so you see that now I want to discuss expectation values of this Wilson loop. Expectation value of Wilson loop is just I divide by z, and here I put the same z with w inside. Right? I just put the w here, and I do the integral, same integral with w over the integral without w. Okay? And you see that when you integrate, let's do the abelian case first. You integrate d phi, right? And you have this exponential of I phi. An exponential of I phi has zero integral, right? It's like integrating cosines and sines. So naively, you would get 0, right? Because you are integrating over this phi. So suppose we are doing this computation, and we are going to see, to ask what this is, at strong coupling, which is at large G. Suppose I think large G, and so I say to leading order, I ignore the action, because the coupling is large and I just ignore it. But then I get 0, because the integral over the phase is 0. How do I not get 0? You see that I don't get 0 from this integral over this phase if I bring down this plaquette here. Because now, with this plaquette here, if the contour has this orientation, and if I multiply by the plaquette that has the opposite orientation, Now this phase that is from the contour will cancel from the phase that is in the plaquette. And this phase that is in the contour will cancel with this phase that is in the plaquette. So when I put this plaquette here, the 0 that I got here becomes 1 at this edge. Before I was integrating it to the I-phi, now I integrate 1. So I get 1. The 0 that I got here now becomes 1. But now I got this guy here, this problem. Now this guy from the plaquette, I get a 0. Well, how do I fix? I multiply by this plaquette here. Now I solve this problem, I solve this problem, and I solve the problem I just introduced, the one at this plaquette. But again, I still have this guy and this guy, that because of these two guys, when I integrate, I get 0. So you see what I have to do? I have to fill everything up, right? I need to multiply to fix this problem. I multiply by this plaquette, then by this plaquette, then by this plaquette, then by this plaquette, and so on. And now that I brought down all the plaquettes, the integral just gives 1. And so what is the result that we are getting? We are getting that this contour is given by the sum. And now, you see, don't be misled by this being in 2D. This is a 3D lattice. There is more than one way of putting plaquettes. I could put plaquettes doing some dome here. That would also work. It doesn't need to be this planar stuff. I drew it in the plane just for help, but it's a 3D thing. So I just imagine it's a contour and I sum over all the surfaces that end on the curve gamma. And what do I get for each of these surfaces? I bring down this term, so I get 1 over 2g squared to the number of plaquettes in the surface. Right? Each time I bring down a plaquette, I pay a factor 1 over g squared. But this is nothing but some integral over all surfaces dy such that y and on gamma of e to the minus some constant times the area of the curve, because the number of plaquettes is precisely giving me the area of that curve up to some number, and this number is related to log of g and so on. And therefore this Wilson loop indeed is given by summing over all possible surfaces weighted by the area of the surface. And so, which one dominates? The minimal area. Right? The minimal area is, everyone else is more suppressed. So this is at least as suppressed as the minimal area, it could be even more. But this will go as e to the minus some constant times the minimal area that is encircled by my contour gamma. And so we are done. We have a theory where now, manifestly, when you put it on the computer, you know that this, if you put a big rectangle, will be proportional to the area of that rectangle. It will not be proportional to the perimeter. Right? We just proved it. Okay? And you could also ask now for quantities that involve quarks and so on, and you will get the picture you expect. That if I have a quark propagating here and a quark propagating here, I will be summing over the surfaces that connect the two quarks, and again they will be suppressed if the distance is large and so on. And so we would say that this model confines. Notice that what we use is the fact that this integral, let's call this d mu, we are using, the key thing that we are using is this notion that the integral d mu of u is equal to 0, and the integral d mu of e minus 1 times u, which is identity, is equal to 1. And so when you have this is the key ingredient. And of course this, you can generalize. You can say instead of integrating over a field, I can sum over plus minus 1. And if I put sigma, it's 0. But if I put sigma squared, now it's 1. And so it generalizes. It doesn't need to be a continuous group like here. It can be discrete, and that's what you were doing. What you are doing is exactly the version of this, where this integral over mu was a sum. It doesn't need to be a billion, like in this example phi. It can be an abillion. It's the same thing. Right? So whenever you have something where the average of the element is 0, like a vector or something, but the average of the square is not 0, you can construct a model like this in the lattice that will exhibit confinement. And then you expect two things. You expect that there is a limit where this model goes to weak coupling and describes the continuum limit, and I can do perturbation theory. And another limit that is strongly coupled, where this model describes confinement. And the quarks now confine, and they cannot be seen in isolation. But this is, of course, super non-trivial to establish. Are these two theories continuously connected? Or is there a phase transition between the two? Is this true that this is a good discretization of my model? And clearly, sometimes it's not. Because you see that here we proved confinement for any gauge group. But QED is not confined. Right? Electrons are not confined. So this derivation is against radio waves, right? Where when we turn on the radio, we see that things are not confined. And so this theory for QED is a theory on the lattice that does not describe QED in the continuum. But this theory for QCD describes QCD in the continuum. Okay? And that's because QCD is asymptotically free, and it allows a lattice discretization where QED is not. So it's a non-trivial question. I naively discretize, and then you ask, is naive good enough? And sometimes it's not. Sometimes naive is just wrong. It's just you are not being smart enough. You are doing something silly because the theory doesn't admit a naive lattice discretization. The theory doesn't have a good UV limit, and you cannot just put it on the lattice. And indeed, so this theory for QED, it's a good lattice theory. It confines, but at large distances it has nothing to do with QED. It's just another theory, one that confines. So that's it. That's lattice QCD. And once you have lattice QCD, if your theory can be discretized, and if your theory admits a lattice discretization, now you have a way of putting it in the computer. Because now you just discretize, you do a 20 by 20 by 20 lattice. Typically people don't do more than that, they even do 12 by 12 by 12 by 12 if it's 4 dimensions, right? I mean, you see, 12 to the 4 is already a lot. And then you just have 12 to the 4 integrations, finite integrations, and then you compute expectation value. Of course, 12 is not a lot. You would like more because you want to see exponential decays and so on. You would like 120, but that's too hard. So you do as best as you can. And obviously, 2D is awesome because things are just L squared instead of L to the 4. And so lattice gauge theory is much harder in higher dimensions than in lower dimensions. But we care about 4 dimensions, of course. So yeah, so this is a paper that started this field of lattice QCD. And already in that paper, he's aware of the power, but also of the need to be careful, because he already points out that, of course, QED is a billion and it doesn't confine, but this gauge theory, for which when it's a billion, still confines by exactly this argument here. Okay, I think that's it. How much time did I use? I felt like I used less time. Yeah, it's okay. It was 1 hour.
Can you do the same thing with showing chiral symmetry breaking on the lattice?
With what? So, chiral symmetry breaking.
Yeah.
Good question. Is there a model on the lattice that makes manifest? That's a good question. I should know, but I forgot. I don't know. It's probably well known, yeah. Yeah, there are many things you can do with fermions. Yeah. So if you bring now correlation functions of fermions, you see that there is a u here. Because of this u, the integral gives 0. So then not to get 0, I need a plaquette. But then I put plaquettes, I need to put many plaquettes, right? So we start seeing that if I have fermions around, I need to put plaquettes, and then I could ask if some fermion bilinears have expectation values and so on or not. And that would be related to chiral symmetry breaking. Yeah, so in the lattice, if you were to compute this in the lattice, you would still have two things you could study in the lattice: short distance things and large distance things. You could imagine I take a lattice and I consider a very big Wilson loop that's with many, many sites, like a 30 by 30 sites, such that it should be a large distance thing. And then I try to numerically study that object and see that it confines and so on, and of course it does. But I can also try to study short distance correlation functions by taking expectation values of fields and making them closer and closer and closer. Like I take two plaquettes, I make trace of f square, and I bring them close, and I see what power law do I get. And to see a continuum limit, I'll need to take g to 0, lattice spacing to 0, and see that I get a continuum limit. And then I hope that the short distance observables, they match with perturbation theory, and I use it to fix my parameters of my simulation. And then, if it does, then the large distance observables give me predictions. The issue is that in QED, the short distance guys will not agree with what I expect, because the theory is not UV complete. Okay, so that's it about this paper. Next week we stay with statistical mechanics, but we'll do something related to symmetry breaking in statistical mechanics, which, as far as I understand, I didn't study the paper yet, is a little bit more involved, so it's going to be slightly more advanced next week, but I think it should be lots of fun. It's something that you probably heard about spin glasses and statistical mechanics of spin glasses, and it's a very tough field, so it's good for us to know something about it. So that's what we are going to discuss next.
Would someone like to give a presentation about some lattice QCD paper? Would you like to give a presentation next week before we start? 15 minutes about some lattice QCD paper?
Okay, try.
Okay, very good. It can be blackboard or slides, since it's about numerics, since it will perhaps involve some plots, you might want to do slides, but up to you. But yeah, so this allows us to put it on the computer, so it would be nice if we could see one plot or one example of something that we could get now from putting the theory on a computer. So if you just spend 10 minutes just showing a plot and explaining how that is obtained in practice, that's enough. Just so we get a flavor of some modern paper doing some powerful stuff with this. Very good. Thank you. So see you next week.
Good. Do you have an opinion on sort of some people argue that confinements due to sort of the center vortex configurations of the field?
Ah, yes.
To me, it's all a bit arcane looking, because they do the computation of the lattice, and then they remove the vortices, and suddenly all confinement's gone. But then, to me, it's I'm not sure if you're just removing more than confinement by doing that. How big is it's hard to define sort of a measure in field space. So how big is really the subset of center vortices and things like that?
Yeah, I've seen that discussed a few times here. What I don't like in what I've seen typically is that they compute not objects that are not gauge invariant. So I would have nothing against doing such games or for Wilson loops. Just don't understand why to do it for some propagator or something that's not gauge invariant. And then you are never sure once you remove stuff. Was it because of gauge invariance or was it because of physics? What happened? So I don't have an opinion because for me, until you first show me something gauge invariant, I don't care. I mean, okay, you did something in some gauge and I got some curve that goes up and it's gauge dependent. But the idea in principle of saying let's try to identify which field configurations are the ones that are generating effectively an area law versus other configurations, and I argue that it's a particular type of configurations, and then maybe they are some vortices that have some particular centers, and there's an effective theory for those centers, and so on. Okay, perhaps. It doesn't seem plausible to me, but maybe. But the first step, I would say, is doing things in a gauge invariant way, otherwise it's, at least for people that are not experts like me, it was silly.
Não, se quisesse, podia discutir rapidinho. Eu queria discutir umas paradas daquele negócio do Zuckerberg, não é interessante. Do quê? O mecanismo lá de Zuckerberg. Que é aquela ideia lá do spin massivo. Eu só preciso vai. Não, então, mano. É bem rápido isso daí, né? Eu tô meio. Mas eu não entendi o que você quer discutir. Tem uma parada meio que tá me incomodando numa parte lá, não sei se discutir vai bem ou não, mas talvez. Mas uma parte do quê? Do final da coisa do mecanismo Zuckerberg lá, que é pra.
Da massa do negócio do voto de.
Isso.
Da de prova?
É. Tipo. A ideia é assim. Você começa com isso, né? Sei lá. QV massivo, né? para P muito grande, esse P quadrado cancela com esse P quadrado e vai com 1 sobre M ao quadrado. Então o argumento que você usa para construir que G0 é normalizável não funciona direito, porque uma das assumpções é que o propagador vai com 1 sobre P quadrado. Então, tipo, se você tiver, por exemplo, um diagrama assim, né? Eu posso colocar mais um aqui e no V isso aqui vai com D4P sobre M ao quadrado, então aumenta a divergência do diagrama arbitrariamente aí não normalizável. Aí a ideia é que você pode introduzir, levar Mi em AMI menos 1 sobre M, dá um Mi φ. E aí a Lagrangiana que você chega é tipo menos 1/4, acho mais que de menos 1/4 F quadrado mais meio de M ao quadrado mais meio de del mi φ ao quadrado mais meio mais a mi del mi φ com M. Acho que é isso. Se eu não me engano, tem algum termo que eu estou perdendo. Acho que é isso. Não, tem um M quadrado aqui, né? Eu acho que é isso. E aí. Eu posso checar aqui, né?
Acho que tá certo, né?
Eu acho que é isso.
Tá certo, tá certo.
É porque o termo cinético vai ser invariante por isso, e aí eu. E aí. Bom, enfim, aí tem essa merda aqui, né? Mas aí a Lagrangiana é invariante por essa transformação de gauge. Então, mi φ ao φ para φ mais m alfa de x e alfa para alfa a para mais del mi alfa. Acho que aqui tem um menos. Não, acho que é mais um coisa. Acho que tanto faz também. Aí, né, tem esse invariante de gauge. Aí o que você faz? Você se mata? Não, você fixa o gauge, né? E aí.
Aí ficou certo.
Não, achei que você não quer negócio inteiro. Aí você fixa o gauge, né? Qual que é a parada? Você usa o FADEF no pod, só que você precisa tomar cuidado, porque você não pode usar. Você pode usar del mi a mi, igual que você normalmente usa. Você normalmente usa uma coisa assim, né? O FADEF no pod. E aí você faz uma média nas funções. E aí você chega naquela merda lá, né? Só que o problema é que isso não impõe fixação sobre φ, né? Você não tem nenhuma. Você não está dizendo nada sobre o gauge de φ com essas coisas. E aí tem uma melhorzinha que é o seguinte: só esse aqui. Aí você vai chegar e você vai pegar essa Lagrangiana, né, e vai somar um termo dessa cara. 2 psi, del mi a mi, mais m φ ao quadrado. Eu acho que aqui tem um menos. E aí. Ou não?
Acho que tem mesmo.
Tem, né?
Sim.
Aqui tem um menos também. Um termo assim, né? Ao invés dos ovos, ficaria sem isso. Aí o que você vê? Olha, você soma. Você fica com uma coisa que é tipo: você abre F. Se você abre F, né? Ele é uma parada do tipo. Primeiro, óbvio, isso aqui, né? Isso aqui é del mi a mi quadrado mais 2m del mi φ, ou 2m del mi a mi φ mais mais m quadrado φ quadrado sobre 2c, né? E aí, o que é bonito, né, é o seguinte, significa a mi deu mi φ menos mais 1 sobre psi, aqui tem um 2 também, não tá aqui, deu mi a mi φ, esse termo com esse, e também com esse termo aqui, né, se você abrir f quadrado, você fica com uma parada tipo enfim integral por partes, você fica com uma parada que tipo a mi p quadrado box gemini menos 1 menos psi pmi pni ani. Exatamente como seria para o fóton, certo? E aí o que você faz? Se igual a 1, desacopla os dois. Porque se pega isso por partes, esse termo fica igual a esse constante menos, se igual a 1, esse termo inteiro morre. E aí fica, o que parece agora? Agora essa teoria parece um fóton, nesse gauge parece o gauge final, um fóton com massa ainda, só que nesse gauge final, que isso aqui vai para zero também. E quando você está com isso aqui é um som escalar. Agora. Sim. Então, isso é escalar com massa. E aí, tudo bom? Aí a parada é que os propagadores agora são isso aqui. Esse termo inteiro vai morrer. Então, 1 sobre m quadrado vai embora. E agora o comportamento é π, 1 menos 1 sobre p quadrado menos m quadrado. Gemini, que é tipo gauge final. E o outro é só 1 sobre i sobre p quadrado menos m quadrado. Porque é um escalar só, né?
Mas esse escalar,
ou seja, a teoria generalizada agora.
eu não tenho uma integral de caminho para o escalar.
Tem sim. Eu não tô.
O escalar não está relacionado à função de gauge?
Então, eu não tô shiftando. Não, calma, é diferente. Eu não tô fazendo esse. Eu não tô tipo shiftando variáveis só, né? Eu tô fazendo uma teoria alternativa. Suponho que eu tenho uma.
Já tem uma integral diferenciada.
Isso, suponho que eu tenho uma teoria alternativa, que é tipo essa, só que onde tinha a mi, eu shifto para mim mais um plano. Ela claramente tem uma liberdade de gauge, que quando eu escolho alfa igual a menos m φ, aí a integral de trajetória, toda dependência em φ some, e a integral de trajetória em φ é redundante. Então, se você quiser, eu posso fazer.
Então, isso que eu ia falar, você tem só uma integral de caminho de φ com uma ação sem ação daí.
Exato. O que eu estou falando é que tem uma escolha de gauge com a dependência em φ fatória e ela reduz para isso. Então tem integral de trajetória para φ.
Não, entendi.
Então a parada é que, se você quiser, aqui em cima estava escondida a dependência em φ dessa teoria como uma constante na frente da integral de trajetória. Conta que essas duas teorias são a mesma teoria, né? Essa teoria e essa teoria aqui, com a integral de trajetória em φ, são a mesma teoria, só que essa é a gauge específica. É uma escolha de gauge daqui embaixo. E aí tem outra escolha de gauge que as coisas são o comportamento dos propagadores é bonito.
Acho que da hora. Eu queria, sei lá, teria que pensar sobre esse negócio aí. Mas acho que não tem nada de errado não.
Eu acho que não.
Não é real, essa integral em φ, ela, na primeira teoria ela cancela todos os observados. Essa integral em φ.
Exato. Ela só vira tipo, eu tinha aqui, né, dφ, e aí S a φ, né? E aí.
Não, mas antes não tinha φ.
Não, aqui embaixo tem isso.
Ah, tá.
Aí eu fiz uma transformação de gauge aqui em A e φ, tal que isso aqui vira só uma função de A. Aí essa integral é inicial,
cancela os observados.
e aí fica uma constante só na frente.
Pô, interessante.
Bem legal, né? Bem chique. E é um Goldstone, né? Esse fio. Ele tem shift symmetry.
Sim.
Do mesmo jeito que o Goldstone tem.
Talvez isso aí seja. Vem de alguma teoria UV aí.
Então, ela é uma forma do método de Higgs, teoricamente. Tipo, é isso que eu falei, é o caso Higgs mechanism. A ideia é que você pega o parâmetro de gauge, não, acho que você leva E para zero e VEB para infinito, mantendo o produto constante. Mantendo o produto constante. E aí, o que acontece é que a teoria, o modo de Higgs da teoria tem massa infinita, e aí ele integra fora e sobra só o Boltzmann. E aí esse limite meio exótico da.
Toda hora, mano.
Legal, né? Eu vou ter essa ideia.
Diferente.
Mas a parada que me incomoda que eu estava falando, né? É que na hora que você coloca essa. Eu não sei, eu tenho que pensar um pouquinho sobre se eu tenho que colocar a interação antes ou depois. Porque se eu não tomo cuidado, é que eu estava abrindo as contas com a interação e eu fico com uma coisa assim na interação. Que é se barra. E aí, isso aqui tem dimensão 6, 5.
E não só.
E aí parece que é não normalizável. Mas não sei, eu tenho que pensar um pouquinho mais sobre isso.
Se aparecer esse termo, parece que você trocou um problema por outro.
Exato, né? Mas não é, porque o resultado famoso que funciona isso, né? Eu só não entendi exatamente como é que eu me livro disso.
O cara vai apresentar essa O cara foi
Imagina.
Não, você poderia falar não, pô.
Não,
Mas eu entendi o que você conta sua vontade.
Tá mais suave do que foi na minha época também.
Tá
Na minha época, tipo, a sua apresentação foi muito boa, mas daí eu perdi muito pouco de tempo no ano passado. Porque era
Você perdeu muito tempo?
Não, você perdeu muito pouco de tempo. Sua apresentação foi muito boa, tanto que o Pedro elogiou. Mas você demorou tipo.
Foi 20 minutos, eu acho.
Então, não era.
É que eles tinham falado que era 10 a 20, eu acho.
Tá, bota fé, não. Na minha era.
Era até 15.
Era
Acho que porque tinha várias pessoas, talvez, né?
Era 10 na real a apresentação.
Caralho,
Era 10. E aí o. E
Você
aí.
foi muito estribado aí,
Não. Tô sendo estribado.
A gente foi estribado. Bom, vamos desligar.
Não, acho que vai ser.
Não,
O único problema de eu fazer isso é que eu não vou conseguir fazer sempre.
Não, tá de boa, mano. Você apresenta. É que assim, eu até queria apresentar nesse peito. Só que você é louco, mano, deu uma moída aí.
Tomara que
Engraçado aí. Pô, mas, mano, eu queria que a gente tivesse dado algum feedback, mano. Não ficou nada.
ele gostou, ele falou que
Você fala, gostei. Foda-se, que eu vou. Sei lá.
Não. Na minha época tinha votação em turma, em público, né?
Eu vou fazer lixo.
Não, tinha umas dessas, não.
Nossa, mano, você é louco. Mas é importante acabando já esse vídeo, porque o próximo paper é o penúltimo. Ele vai apresentar esse próximo. E eles são mais dois.
Ué, não, 8 papers?
Então eu diminuo pra 5. Porque.
Eu acho que tem, provavelmente.
Mas eu falei pra ele, pô, e aquele fenomenológico agora? Não tem nada pra fazer. Mais um.
Qual que é depois desse?
Você diz, tipo, a semana que vem?
Depois do semana que vem.
Depois da semana que vem.